Welcome back. Hopefully that last week for you was at least a little bit restful. We're going to jump right back in now with Unit 9, Lesson 6. This is actually the last lesson of the unit. And we're going to talk about something called Le Chatelier's principle. Okay, so the intention for today is to predict the result of applying a stressor to a chemical reaction at dynamic equilibrium. Okay, remember dynamic equilibrium from the last lesson. If you need to review that, definitely check out the last lesson again. But I'll give you a quick review right now. Basically, right, dynamic means there's motion, and equilibrium, right, something is equal. In this case, the thing that is equal, if we're talking about a chemical reaction, remember that a chemical reaction can go forward and backwards. Okay, and if a system's at dynamic equilibrium, the rate of the forward and reverse reaction, that's the thing that's equal. So the forward reaction is happening at the same speed or the same rate as the reverse reaction. That's dynamic equilibrium, right? And when you're at dynamic equilibrium, it looks like nothing's changing because the concentrations of the substances that are involved are not changing. All right, so the two key points for dynamic equilibrium, concentrations don't change, right? Careful, they're not equal. They just don't change. And the rate of the forward and reverse reactions is equal. Okay. So before we move on any further, go ahead, pause the video, and try a couple questions. You got a pretty straightforward one, and then a nice review question, multiple choice style. So go ahead and pause and try that out. Okay, so why did I ask that first question, right? What do you do to relieve stress? Well, the whole point, and you could probably come up with a few different things, right? But the whole point of that question is because that's what we're going to talk about today. Le Chatelier's principle tells us what a system at dynamic equilibrium will do when it's put under stress. Now, the way you stress a chemical reaction or a system at dynamic equilibrium is a little bit different than the stress we feel. We'll get into more detail in a bit, but the different kinds of stresses are like temperature changes, concentration changes, pressure changes, if it's a gas. Okay, so the same idea that when you're feeling stressed, you make a change, you do something to change what's happening. Well, systems at dynamic equilibrium, when they get stressed, they also change. They do something, and they respond to those stresses. Okay, number two, a good review here. It's been a while, right? So the enthalpy for the following reaction is given, right? That's our delta H here is enthalpy. Looks like negative 483.6 kilojoules for this reaction. I recognize this, right? This is hydrogen gas, oxygen gas making water. It says, which of the following describes this reaction? Well, so first thing, right, I have to decide between exo or endothermic. And this is kind of a memorization thing, right? Something you got to know is that if the delta H is negative, as it is here, that means it's an exothermic reaction. Okay, so negative delta H is exothermic, a positive delta H is endothermic. Okay, so a way to think about that is like, right, it's the change in energy. So if you have a negative change in energy, that means you're losing energy. That's exothermic. Okay, so this is an exothermic reaction, and so we're deciding between A and B. So which side? It's basically asking now, where would we put the energy term in an exothermic reaction? Well, exothermic, like we just said, means energy is coming out, right? Or you could say energy is produced in the reaction, even though it's not, created or anything, right? You can't create or destroy it. So if it's released from the reaction, if it goes out, that means it has to be on the product side, right? This is the product side. This is the releasing side. This, if it was over here, would be endothermic. It could be going into the reaction as a reactant. But negative delta H means exothermic, and we add it to the product side. So the answer for that one is B. Okay, so hopefully that was a good review. I believe that, that was lesson 1. All right, lesson 1 in this unit. So that's from the very beginning of the unit. It's definitely good to go and check back on that because later this week, right, I'll be putting out the unit 9 assessment. Okay, so let's get into it. What is Le Chatelier's principle? Well, it's right there. When a system at equilibrium is subjected to a stress, the system shifts in order to relieve the effects of the stress and restore equilibrium. Now, this is not just a thing in chemistry, right? This principle extends beyond that. Now, you could probably, I'd like you to try to come up with some examples. I'll give you one example so you can come up with some on your own. So, say you have, in your house, you have a thermostat that controls the temperature, right? If you control your own heat. I don't in my apartment, so I don't have one of those, but lots do, most do. Now, say the temperature is set at, and we'll do Fahrenheit, okay, the only time we're going to do Fahrenheit. The temperature is set at like 72 degrees Fahrenheit, okay, pretty comfortable temperature. Now, it's at equilibrium, right? But what if, say, I turn the stove on or the oven on and I leave the door open? Now I have all this heat kind of entering the room, right? I'm stressing the system at equilibrium by increasing the temperature in this case. So what's going to happen? Well, the thermostat, or the heating and cooling system of the house, right, it'll sense the temperature change, and it'll do something to restore equilibrium. So how do we restore that equilibrium? If the oven door is open and it's getting hotter, the AC turns on, right? So now we have to make it, the system changes in order to restore equilibrium and bring it back to that 72 degrees Fahrenheit point that we want, okay? Now, if you leave the oven open, right, the AC is going to have to keep going and going and going. But that's dynamic equilibrium, right? We have the oven creating heat. We have the AC unit turn on to cool down the air. Both reactions or both processes in this case will be happening simultaneously, but at the same rate, so that the temperature won't change, right? So we keep that equilibrium at 72 degrees Fahrenheit or whatever, okay? So anytime there's equilibrium and the system gets stressed, something's going to happen to restore equilibrium, right? We're going to kind of try to offset whatever happens. So see if you can come up with some other examples there. Note, right? When equilibrium is restored, right, it's a new equilibrium point because the conditions have changed, right? In our example with the house, that AC is now going to have to just be on all the time if you leave the oven open, right, to counteract the heat from the oven. So the new equilibrium, right, has the AC pumping at a higher rate. So you're at a different, right? That wasn't happening in the house originally before the oven was open. Okay. Okay. But moral of the story here, just this top sentence, if this makes sense, right? System at equilibrium, it gets stressed, something is going to happen to restore the equilibrium, right? You're going to do something to counteract the change or the stress that's occurred. So if we're talking about chemical equilibrium, right, we're going to examine how the system shifts when there's a change in the following: concentration, either of reactants or products, the pressure/volume. Now that's going to be the same thing. If we're talking about gases, right, I'll do a little review on the relationship between pressure and volume. But if we decrease the volume, right, we're going to increase the pressure. It's that inverse relationship. We're also going to look at how a system at chemical equilibrium will shift in response to changes in temperature. Now, when I say shift, right, it's really important that we understand what I mean when I say the word shift. So remember, right, in dynamic equilibrium, we have reactants on the left, products on the right, always, okay? So if we say that a chemical system shifts to the right, what that means is we're going in this direction, from left to right, and that means reactants are being used up and the products are being formed. Okay, so shifts to the right, we do the normal left to right, reactants to products. If we say a chemical system shifts to the left, that's the reverse, right? What's actually happening is we're having products turn back into reactants, okay? At a higher rate, right? Remember, at equilibrium, both are happening constantly, right? Reactants are turning into products are turning back into reactants, and that the rate of those two processes is equal. When we say it shifts to the right, that means more reactants are turning into products than going backwards. And if we say a chemical system shifts to the left, more products will turn into reactants than the other way. Okay, definitely, pause here, review this material, because this is kind of like the foundation for this next part. You have to know what I'm saying when I say shifts to the right or shifts to the left, right? It's just basically which shifts to the right means the forward reaction is favored. Shifts to the left means the reverse reaction is favored. Okay. So what is the effect of concentration changes? So if we increase the concentration of a substance, it's going to get used up. It's going to the system is going to shift away from that side. Okay, I'll go into more detail in a moment. If the concentration of a substance is decreased, or you kind of remove it, it's going to get replaced. It's going to shift toward that side. So it's easier to see with an example. So here's the example from the do now. Okay, I put the energy term in there this time, right, because it's exothermic. So we have, right, hydrogen and oxygen turning into water and releasing energy. So what would happen if the chemical equilibrium above was subjected to the following? And these are called stresses, right, or stressors. What happens if the concentration of H2 increases? So if I increase the concentration of H2, it's going to get used up and shift away from that side. So it's going to, since H2 is on the reactant side, the reaction is going to shift to the right and create more products and release more energy. Okay, so if I increase the concentration of H2, it's going to shift away, shift to the right. And if I decrease the concentration of H2, right, it's going to get replaced. And the only way to replace the H2 is to shift the reaction to the left. Okay, so to take this water and break it back down into hydrogen and oxygen gas. Okay, so if I decrease the concentration of H2, I'm going to shift this reaction to the left to create more H2, right? Remember, it's always about counteracting the stress, all right? So if I increase the concentration of O2, okay, it's going to be the same as the H2 because they're both reactants. So if I increase this concentration, it's going to get used up, shift to the right. If I decrease the concentration of O2, right, I take some of the O2 out, then the reaction is going to shift to the left to replace the O2 that I've taken out. So H2O will break up back into hydrogen and oxygen gas. Okay? What happens if I increase the concentration of H2O? Now, since H2O is one of the products, and if I increase it, right, it's going to get used up. That means the reaction will shift to the left. Okay? Always, right, if you're increasing, it's always going to shift away. If you're decreasing the concentration, it's always going to shift toward that side. So since in number 5 here, we're increasing the concentration of H2O, the reaction is going to shift away, and away has to be to the left. Okay, which means, right, if we decrease the concentration of H2O, if we remove H2O, and we decrease the concentration, then the reaction is going to shift toward that side, which is the right side. So the reaction will shift to the right to replace the H2O that I removed. Okay? So a lot going on there, right? But it's pretty straightforward. If you take something out or decrease the concentration, it's going to get replaced by shifting toward that. The reaction will shift toward that side. If you add more of something, it's going to get used up, and it's going to shift away from that side, right? Okay. Add more H2 or more O2, it'll shift to the right. Add more water, it'll shift to the left. Take away H2 or O2, it'll shift to the left to replace it. Take away H2O, the water here, it'll shift to the right to replace it. Okay? Okay, next is effect of pressure / volume, right? So I'm combining these. We can just say pressure or volume. We could talk about either one. And again, this is only going to apply to gases because if you change the volume of a liquid or solid, you're really just changing the concentration because you have to add more. But gases, right, can have all kinds of different volumes because they take the shape of their containers. Okay, so remember, right, pressure and volume are inversely related, meaning if I decrease the volume, I increase the pressure, right? If I squeeze a balloon and decrease the volume, the pressure is going to increase and it's probably going to pop, okay? So an increase in pressure will cause a shift toward the side of the reaction with fewer gas particles, right? So if I increase the pressure, the reaction is going to favor the side with less gas particles or fewer gas particles to relieve that pressure. If I decrease the pressure, it'll do the opposite. The reaction will shift toward the side of the reaction with more gas particles. Okay, so we'll look at this same reaction again. Now we have all gases here, so this applies. Now what would happen if I did the following? If I decreased the volume, right, which means I'm increasing the pressure. Well, if you look on our reactant side, we have 3 moles of gas, right? 2 hydrogen and 1 oxygen. 3 moles over here, only 2 moles of gas over here, and it's just H2O. So the products have less particles of gas. So if we increase the pressure, we're going to favor the side of the reaction with the least gas particles, which is the product side in this case. So we're going to actually end up making more H2O. Right? So if I have this reaction and it's at equilibrium and I increase the pressure by decreasing the volume, it's actually going to cause the reaction to make more water because this is the side of the reaction that has less gas particles or fewer gas particles. So, right, if I increase the volume or decrease the pressure, okay, it's going to favor the side of the reaction that has more gas particles because more gas particles is going to help the pressure go back up. Remember, anything we do, the system's going to react to counteract whatever we do. So if I decrease the pressure, it's going to favor the side with more gas particles because that'll cause more pressure, right? So if I decrease the pressure, the reaction will shift to the left and will actually make more H2 and O2, okay? All right, and remember, I'm going kind of fast, so you can always pause, rewind, watch it again, okay? All right, how about temperature? So, increasing, this is where it's important. We got to know where the energy term is, right? So increasing the temperature will cause a shift toward the side of the reaction without the energy term. Decreasing the temperature will cause a shift toward the side of the reaction with the energy term. So here's our reaction again, same one as before, system at equilibrium. What would happen if I increased the temperature? Well, if I increase the temperature, it's going to cause a shift toward the side of the reaction without the energy term. So increasing the temperature is going to favor this side without the energy term, and I'm going to end up making more reactants. I'm going to make more H2 and O2. Okay, and this is going to get used up, right? Now, if I decrease the temperature, okay, it's going to favor the side with the energy term, right? Think about it. If I decrease the temperature, how does the system raise the temperature? Well, you make more energy, or you do the exothermic reaction. So if I decrease the temperature, it's going to cause the reaction to shift toward the energy term, which is on the product side, and we're going to end up making more water and releasing more energy to counteract that decrease in temperature. Okay, so I know that was a lot, all right? And that's going to be it, right? So we talked about if we add or remove substances, which is decreasing the concentration. We talked about changing the pressure, and we talked about changes in temperature. Okay, all of those things will have an effect on a system, and I suggest going back and reviewing those 3 slides I just went through before trying this check for understanding. Okay, so go ahead. You can pause the video here, try this out, and then unpause me and I'll go through it. Okay, so number 1 is done for us, right? So in this case, right, we're looking at a different equation now, right? We have N2 gas, O2 gas, plus heat makes 2 moles of NO. Okay, so if I add N2, it's going to shift to the right, right? If I add to a side, it's going to shift away, so it's going to shift to the right, and the amount of NO, well, that's a product, so it'll increase. Okay, this first one is good. What if I take away some of this? Take away O2. Well, that means it's going to shift toward that side. So it's going to shift to the left, okay? Let me write that in there for you. Right, it's going to shift to the left, okay? Which means, and it's asking about how much N2 is it going to make? Well, if we're shifting to the left, here's the left side, that means we're going to make more N2. So that's going to increase. Okay. What happens if NO is removed? Okay, so if I take away NO, right? If you take something away, it's going to get replaced. So how do I replace the NO? I shift the reaction to the right, okay, so to make more NO. So the reaction is going to shift to the right. Oh, almost a good arrow. Okay, and what happens to the amount of N2 in this case? Well, if I'm shifting to the right, that means all of this stuff over here is getting used up, and this is being created. So N2, since it's a reactant and I'm shifting to the right, it's actually going to decrease the amount of N2. not going to write the whole word. Okay? All right, number 4. What happens if heat is added? Okay, so if we add heat, right, that means we're increasing the temperature. So it's going to favor the side of the reaction that doesn't have the energy term. Okay, so since that would be the product side, right? See the energy term in this case, it's on the reactant side, right? If we add heat, it's going to favor the side of the reaction without the energy term, which is the product side, which means we're going to shift to the right. Okay, and if we shift to the right, how does that affect the amount of NO? Well, since NO is on the right and we're shifting to the right, it's going to increase the amount of NO. Okay. All right, last one. Let's see. Pressure is increased. Okay, right. Pressure. That's a weird one. That has to do with gases. Oh, right. If we increase the pressure, it's going to favor the side of the reaction with the fewest amount of gas particles. All right, so if I look here, I have 1 mole of N2 and 1 mole of O2, so that's 2 moles of gas particles. And then over here I have 2 moles of gas particles. Okay, so it's equal. So this one's a trick, right? So you probably got stumped on this one. So because both sides of this reaction have the same number of moles of gas particles, right? 1, 2, right? Remember that these are 1s in here. So 1, 2 on the left and 2 on the right. That means the reaction is not going to shift at all because there is no side with fewer gas particles. Both sides have 2 moles, right? 1, 2, and then 2 of gas particles. So there is no shift because sorry, it takes full concentration to write on this thing. Okay. There is no shift because there is no side with fewer gas particles. If there was a side, it would have shifted toward the side with fewer gas particles, but there is not, and that means that the concentration of O2 doesn't change. No change. No change. Okay, so go ahead and yeah, I really can't talk and type this at the same time. Okay, so go ahead and try the challenge question, or you can review this question. Watch me go over it again, right? Make me repeat myself a million times if I have to. Or you can try this challenge question. I'm going to answer that in a sec. I'll give you a second to pause if you want. Okay, so challenge question. How would the addition of a catalyst affect a reaction at dynamic equilibrium? Explain your answer. So this one's pretty tricky. So remember what a catalyst does. It lowers the energy of activation, the activation energy for a reaction. But not just the forward reaction, also the reverse reaction. So a catalyst actually will have no effect on dynamic equilibrium because it'll speed up the forward and reverse reactions equally, right? So you have a system at dynamic equilibrium, right? Forward and reverse reactions are equal, and you speed up both equally. That means they're still equal, so nothing's going to happen. So a catalyst actually does not affect a reaction at dynamic. That's not a stressor, I should say. It speeds up both reactions equally, so you're still at dynamic equilibrium. Okay, cool. Definitely review this lesson, and there is another homework assignment. This is the last lesson in the unit, so we'll have a little extra time to talk about this stuff during office hours. Okay, all right. See you guys later.